This is going to be the last video on the carboxylic acids and derivatives chapter. When we talk about reactions with carboxylic acids, it must be in its acidic form. Meaning if we're comparing these to our other groups, we're saying that we know that they're more reactive than amides, but if they are deprotonated, they're actually the least reactive species we'll see in this chapter. So carboxylate ions are not going to react with nucleophiles. Once that negative charge is on an oxygen, you will not be able to have a nucleophile that can come in here because you'd be placing a second oxygen with a negative charge on that carbon. Reactions with carboxylic acids can happen under acidic conditions, and if we add an alcohol to them, we can turn them into an ester. You would exchange your OH for your methoxy group here. This is going to be catalyzed by acid, meaning having that acid on there, and excess alcohol will actually drive this to the right. When we have a carboxylic acid and an amine, we actually have an acid-base reaction in which that nitrogen is going to deprotonate the acid, making a salt. You would not have any nucleophile here. The nitrogen is lost as lone pair, and you don't have an electrophilic carbon anymore, because it would have two oxygens with negative charges on them. So if you have an carboxylic acid and amine, an acid-base reaction is going to happen. Amides do react if you have acid present. So if we add a water, acid, and heat to an amide, we actually can see we have a carboxylic acid. This version is going to be protonated because we still have acidic conditions, and that's why our nitrogen does not act as a nucleophile to prevent this from going backwards. If we use an alcohol, we can create an ester. And again, notice here that our nitrogen is still protonated to prevent it from being a nucleophile. The first step for both of these is going to be protonating our oxygen. This should remind you of what we did with esters. Here we have our hydrogen being grabbed from the oxygen. We now created a more electrophilic carbon and prevented having any negative charges on our oxygen, especially considering we're in acidic conditions that wouldn't happen. We have added a neutral nucleophile, so your next step should be to deprotonate. I have seen mechanisms where the nitrogen is what's used to take the proton away, because that's going to be your next step. So if you wanted to combine these two steps, I have seen that being shown. It would depend on what was learned in class. Notice here, same thing with esters. We can have either one of those OH groups pick up the proton instead. We really wouldn't see that as much because we know nitrogen's a better base, but if we did, we can just reverse back to our amide starting point. We now have a much better leaving group. We can have the oxygen kick its electrons down to kick out our positively charged nitrogen. Our nitrogen is still going to be basic. It can even come back and take the hydrogen away from our carbonyl oxygen, giving us our protonated carboxylic acid and our protonated amine, preventing it from being a nucleophile. The weakest base is going to be your best leaving group, so protonating that nitrogen in that step before kicking it out allows you to have a much weaker base, right? If we kicked out NH2-, that would be a much stronger base. So here we're going to say that our protonated amino group is going to be a weaker base than the hydroxide ion. So while we've never seen OH- as a leaving group, our NH3 group can. Another reaction often talked about in this chapter, and we talked a little bit about this in the ketones and aldehydes chapter, but we can now go through the mechanism of how it happens. Acid catalyzed hydrolysis of nitrile groups actually turns them into carboxylic acids. Let's talk about this mechanism. The first part is going to involve the lone pair of the nitrogen picking up a hydrogen. We know this is going to be acid hydrolysis. That will create a positively charged nitrogen, and I want you to look at these two arrows. They seem to be new and different, but what they really are the same arrows we've been drawing, except going from a double bonded oxygen to a triple bonded nitrogen, right? Our oxygen still acts as a nucleophile towards that carbon and pushes it out onto the nitrogen. That's why this mechanism is often included in this chapter. At this point, we have a positively charged group coming off of our carbon, right? With a neutral nucleophile, we will always have to deprotonate in the first step. I've often seen, again here, the nitrogen being the one to grab that hydrogen, since that's going to be the following step. Here I have the nitrogen picking up another hydrogen from the base that just picked it up off the water. At this point, you can have the nitrogen having a positive charge, meaning that my double bond oxygen can push down, and I now have created a resonance contributor for a protonated amine, right? That looks an amide. It looks like we have the double bonded oxygen, and when we do several steps, which essentially is amide hydrolysis, we can turn that into a carboxylic acid. So if you combine the first mechanism we talked about and this one, you can go all the way from a nitrile to a carboxylic acid. Other things that you can do with nitriles, you can turn them into nucleophiles, having an SN2 reaction with a haloalkane, kicking off the bromine. Now you can turn this into the nitrile. Acid hydrolysis is going to turn that into the carboxylic acid. Other reactions, and we talked about these before, you have a nitrile group. When you add hydrogenation to that, we can turn that into a primary amine. The last functional group I want to talk about is known as an acid anhydride. And if you look at it, it's really two carboxylic acids getting smushed together, removing one hydrogen and one OH group. So an anhydride, meaning we've removed one molecule of water. These are going to be very reactive species, and we put them sort of right after acid chlorides. Esters, carboxylic acids are about the same, and amides are going to be your least reactive. And so some of the reactions they can undergo, the arrows are going to be very similar to our other carboxylic acid derivatives. If we end up using an alcohol as a nucleophile, we can chop that in half, making a carboxylic acid and an ester. If we use water, we can turn that into two carboxylic acid. If your R groups are the same, then you would have two of the same thing. And if you use an amine as a nucleophile, you actually can turn it into an amide, as well as the deprotonated carboxylic acid, because we already have a second equivalent of amine there. Arrows for this, we'll start with a neutral nucleophile one. If we have a alcohol, we can use the lone pair on the oxygen to push into electrons at the electrophilic carbon. Notice here it doesn't matter which carbon you attack since they're the same. These arrows are the exact same as the rest of these mechanisms. Since we have a neutral nucleophile, the next step would be deprotonation, taking off that hydrogen before you go any further. At this point, we now have a nice leaving group. Our oxygen can come down, push this out. This is where we're going to turn into our two pieces. If we're under acidic conditions, which we've generated from our base, we can actually have protonation of our carboxylate anion turning into our ester and our carboxylic acid. Often carboxylic acids are activated, meaning that they become more reactive and used in synthesis. One of the reagents that can do that is PCl3. The other one you learned about may have been thionyl chloride. They do the same thing, replacing a OH or even a carboxylate anion with a halogen, either chlorine or bromine. So thionyl chloride will be the other one. If you have an acid chloride and an alcohol, you can turn that into an ester. So this reaction is a little bit cleaner, a little bit higher yield than going from a carboxylic acid to an ester. So you'll often see going from a carboxylate anion or a carboxylic acid to an acid chloride or an acid bromide, and then continuing your reaction. You can do the same thing. We already talked about these reactions before, but once you have your acid chloride, you can react it with an amine to get an amide. That is